Good evening, my dear NEET warriors. Welcome to yet another session of NCERT line by line, where we decode the NCERT, not just for your boards, that's your class 12th examination, but also for the NEET examination. And we know NTA paper setters, they sit with the NCERT and they frame the questions. In fact, there have been so many instances where in-text questions, exercise questions, NCERT lines have been directly picked up, and majority of the paper we know is going to be very pretty much straightforward. Yes, there will be tricky questions. At least the straightforward part you should be able to crack it, right? So yes, the next chapter 9, ray optics, will be doing part 1 today. Part 2 I think we'll be doing in the next week. It's a big chapter, so I don't want to rush it up. I hope you guys are okay with it. And quickly smash the like button if you haven't done that, and subscribe to the channel. And let me also remind you very quickly that as you are watching this video, please smash this like button. Yeah. Even if you are watching it recorded, do that right now. And more so ever, if you can't comment and write, yeah, please, I mean, in the live chat, because you might be watching it recorded. So then put it up in the comments. Live students so are there. Hi, Madhumati, Nishita, Ria, Kingi, BVKS, Krishna. Welcome. Let me also remind you that your NEET 𝐂𝐿𝐤 batch, there is basically, skip ads, okay. Yeah, there is basically an entrance test for the scholarship which is going on this particular Sunday. So make sure you click the link which is pinned in the chat box. Also, the link will be there in the comments as well after this session. So this scholarship test is on 24th November. Make sure in the evening. So make sure you give it, because you can win up to 13,000-14,000 worth of scholarship based on your score. And it's not very big score that you need, 300-400 marks out of 720, you get that much scholarship. So I'm pretty sure you'll be able to crack it. This is one flagship rigorous batch where you have obviously the best teachers, best training, and you have a very quality level content right from the beginning with one-on-one mentorship. So this is the 𝐂𝐿𝐤 program. Make sure you check it out. More details about it I have mentioned in another video yesterday, so you can check it out. Yes, right over here on the channel. Score Stuck in NEET. This is that video which you need to watch regarding the 𝐂𝐿𝐤 program. All right, cool. So let's begin with the class. I'm very good, Krishna. And wave optics after this, thermal properties later on. Ria, good evening, evening star. Hi, Gangaraju. Welcome. Wave optics will master with me only. Okay, let's begin. Yes, all the warrior Pandus live. Hi, Mardei, nice to see you. Yep. So let's begin with the class. So, my dear warriors, in this particular chapter, see, you will see chapter 9 is ray optics, chapter number, 10 is wave optics. They are two different things, but they are related to light. In ray optics, you are mainly concentrating on how the rays of light travel when they encounter a reflecting surface or they encounter a different medium. When they encounter a reflecting surface, that phenomena is called as reflection of light, which you see yourself in the mirror most of the days, correct? Or maybe the rear view mirror of the vehicle. So these are reflection based phenomena. Refraction based phenomena is where the light goes from one medium to the other medium. Example, you wear a lens, or you see through a glass, or you see what is under the water. That is a refraction based phenomena. This is what you study in this particular chapter number 9 of ray optics. You show the rays of light which go, and you see how the path, what is the path that they take, what kind of image is formed, where is it formed, where will you see it, how big is it as it is, or is it been inverted. That is what you are more interested in this chapter. Whereas the next chapter deals with another property of light, which is called as wave property, and wave property is way different. We'll talk about it in the another chapter, which is chapter number 10, right? Okay, that is what has been mentioned in this particular part. Speed of light they have given, etc. Okay, and we have also seen electromagnetic waves, chapter number 8, where light actually travels like an electric field and a magnetic field wave, both of them perpendicular to each other. The direction in which that electromagnetic wave goes, the direction in which that electromagnetic wave goes is basically, that path is called as the ray of light. That path is called as the ray of light. Yes. Yeah. All right. So the path is called as the ray of light, and the bundle of such rays becomes a beam of light. So when I have a torch, it's not one ray, two rays, three rays, four rays. There are many rays bundled, collected together. So then it is called as a beam of light. So like I said, in this chapter, we will consider the phenomena of reflection, refraction, and a little bit of dispersion of light. Okay, and we'll use basic laws of reflection and refraction, and we'll see how the image is being formed in this particular thing. Also, the last part deals with optical instruments. Is that right? Okay, awesome, awesome. Right. 𝐂𝐤 already have made a video on fluids on the JE channel. You can just search my nurture videos. Please watch that. It is really, really going to be helpful for you. Okay, because it's a very low weightage one. Okay, cool. So now talking about reflection of light, that's section 9.2. Here they basically describe about what is that law of reflection, and this is something which you have studied back in which standard? 10th standard. I hope you remember it still. Yes, when light falls, that is called as incident ray, and the rebounded light is called as reflected ray. The reflecting surface is usually called as the mirror, and the perpendicular drawn to that reflecting surface is called as the normal. There is an angle which is made by the incident ray with the normal, that is called as the angle of incidence, and the angle which is made by the reflected ray with the normal, not with the surface, that is called as the angle of reflection. These two angles, theta, theta, they are equal. That is basically the law of reflection, where the angle of reflection and basically equals the angle of incidence, and they have defined what the meaning of reflection angle is: the angle between the reflected ray and the normal, and the angle between incident ray and the normal is called angle of incidence. Also, the second thing is, this ray, this normal and this reflected ray, all three of them will be in the same plane. It will never be like incident ray came here and reflected somewhere else, or normal is in some weird plane. No, they will all be in the same plane. So the incident ray, the reflected ray, and the normal to the reflecting surface lie in the same plane. That is the second part of the law of reflection. Now, these laws are valid at each and every point on the reflecting surface. This is very important. These laws are valid for each and every point on the reflecting surface, whether plane or whether it is curved. But in this particular NCERT or in this particular syllabus, we restrict ourselves to curved surface. What do I mean by that? See, here whatever reflection has been shown is for a flat surface. Maybe the surface is curved like this, or maybe it is curved like this. So if by chance light enters over here like this, it will, if light enters over here like this, it will reflect back like that. Same thing here also, if it falls like this, it will reflect back like that. If it falls like this, it will reflect back like that. If it falls over here like this, it will reflect back like that. Everywhere you can apply these laws, whether it is a flat surface or whether it is a curved surface. This is flat, this is curved, so it is valid for all shapes, sizes, or curvatures. I hope this is absolutely clear. Correct. All right. Now, next thing that they have also told, we will be already discussed geometrical center of a mirror called as the pole. Okay, so here they have redefined what is the meaning of the word, pole, whereas that of the spherical lens is called the optical center. The line joining the pole and the center of curvature of the spherical is known as the principal axis. The principal axis is the line joining the optical center with the focus, as you'll see later. So I'll just revisit this definitions in case you have forgotten it from 10th standard. Obviously, you might have forgotten. So see guys, there are two kinds of mirrors that we usually see in spherical curved mirrors. Normally, if it was a flat mirror, then what would happen if I am standing in front of it? Let's say we take a penguin from Antarctica. If a penguin sees itself, it will see itself erect. It will see itself of the same size. It will see itself exactly at the same distance inside as much as it is standing in the front. That would be for a plane mirror. This is a plane mirror. This is how the light rays are getting reflected, and the image which is formed over here, which kind of an image it is? It is a virtual image. Now you might be wondering, what the hell is this virtual image? If you have forgotten, virtual image is an image which you will be able to see directly. Number one, you can't see it on a screen. Number two, number three, main thing is, you will see that the rays are not going to meet after reflection. Rather, you have to extend it backwards for them to meet. When you have to extend the rays so that they meet and form the image, that's when the images are always virtual, be it mirrors, be it lenses, be it telescopes, be it microscope, anything, doesn't matter. So whenever the rays actually don't meet after reflection, refraction, then the image is not real in nature, it is virtual. That means wherever you extend it and you see them meeting, you will feel it is virtual. You will feel that something is there over here. Because if these rays, just imagine if I show many rays coming like this, when these rays enter my eye, my brain will start processing and think, oh, these rays are coming from here. So it will automatically create a picture of this penguin in my head. Remember, this picture is not there in reality. It is only there in my head. My brain perceives it as if there is some image over here. That is why it is said to be virtual. So even if you go behind the mirror, you do something, you put something else, nothing will happen, because actually nothing is there. Actually nothing is there. That's why it's called virtual. Whereas in case of a real image, the rays would have merged over there. And if the rays actually physically merge, then if you hold a piece of paper, cardboard, or some sheet, you will see the image formed on that particular sheet. Example of a real image, best one, the cinema hall. You would have, I hope you remember the cinema hall. These days people generally sit on Netflix, Prime, or YouTube. Well, remember that cinema theater? So there is a projector, and that projector projects light, and it falls on a big screen. And those are the points where the rays of light actually physically meet, and you are able to see an image being recreated on that screen. That is a real image, and that is obtained on a screen. Is that absolutely clear, everyone? Yep. I'll make a separate strategy video for 150 marks in physics. Don't worry about it. Yep. For now, I hope this is absolutely clear. Now, my dear students, coming back to curved mirrors. So this is a curved mirror, like you can see over here. This is obviously a curved mirror. The curvature is there. Now, there are different types of curvature. If it is a flat mirror, that we don't have in syllabus, okay. So this is nothing but a concave mirror, because the light rays is reflecting from a surface which looks like a cave where olden people, I mean, long thousands and thousands of years back, people used to stay, or a lion or a tiger stays in a cave. So cave, concave, the light is reflecting from the cave, so concave. And if it is convex, it looks like this. Vex, it bulges. Vex means it bulges. Okay, so this is the bulged out surface. So the light rays are reflecting from that bulged out surface. So that's a convex surface. So it's a convex mirror. So this is how the reflection occurs in the convex or in the concave mirrors, which are also called spherical mirrors, because they look like a sphere. I hope you can see that. See, right now it might not look like a sphere, but actually if you keep on extending it, it will complete a sphere. Same thing over here also. it might not look like a sphere. It is actually an arc. If you keep on extending it, it will become a sphere, guys. So that is why, since they are a part of a bigger sphere, that is why they are called spherical mirrors. They are called as spherical mirrors. So as you can see over here, this is a convex mirror. The reflecting surface is over here. This is a concave. The cave is inside. So the reflecting surface is here inside that cave. Next, the mirror will have a center. The center of the mirror is called as the pole, not the center of the sphere. If you divide the mirror into two equal halves, the center of the mirror is called as the pole. Okay, the center of the mirror is also called as the pole. Okay, then if you take that imaginary sphere, the center of the imaginary sphere is called as the center of curvature. The radius of that imaginary sphere is called r, which is the radius of curvature, correct? And the line which goes from the pole to the center of curvature, pole to the center of curvature and pole, that line, okay, which basically symmetrically divides the mirror or the lens, that line is called as the principal axis. That is called as the principal axis. I hope this is clear. Absolutely. Very good. Next, there is also another point called as focus. We'll come to it. Focus is the point where the rays appear to meet or actually meet. So I'll show that as well to you. Don't worry. But I hope these basic definitions are absolutely clear. Pole, optical center, the principal axis, okay, radius of curvature, and all of that. Okay, great. Now, coming to the sign convention part and also to the focal length. I think focal length is there on the next thing. Okay. Now, first coming to the sign convention part. This is very crucial. Let me tell you, the sign convention plays a very important role in not just mirrors, but also in lenses and everywhere. If you make a mistake in the sign, no matter how correctly you do it, you will always generally get a wrong answer. So make sure the signs are correct. It is not as simple as right side is positive, left side is negative. That is very stupid way of looking at sign convention. Wrong. In fact, how it goes is basically everything is measured from the pole. Okay. This is a Cartesian sign convention. You can see Cartesian sign convention. According to this, all the distances are always measured from the pole of the mirror. Always from the pole. That means that point which divides the mirror into two equal parts. Okay. The distances are measured in the same direction as the incident light. This is very important. Measured in the same direction as the incident light are taken as positive, and those measured in the direction opposite to the direction of incident light are taken as negative. So very important, who is positive and who is negative. Okay. Also, next important thing about height, heights measured upwards are basically with respect to the normal to the principal axis are taken as positive, and next thing, the heights measured downwards are taken as negative. Okay, so this is basically the sign convention. Now let me help you with that. Imagine there is some object kept over here. The object will emit rays. The rays will go like this. It will fall on the mirror this way. So because it is falling on the mirror this way, so this side of the mirror is positive, the opposite side is negative. Always look at incident light, simple. And whatever is up is positive, whatever is down is always negative. Very easy peasy lemon squeezy. Wherever the incident rays are going, if it is going like this, the mirror will now divide into two spaces, this side and this side, because the light was going this side. So this side will be positive, this side will be negative, as straightforward as that. Okay. The low weightage chapters will be taken up in the crash course for the JEE. Don't worry. Okay. It's already a part of the crash course. So if you are a part of it, it is already done properly. Number two, in detailed classes of all the chapters is there in VBuddy, my classes. All the chapters, the entire 11th and 12th standard syllabus, I have taught detailed, taking proper time in the VBuddy, which is a part of the crash course. If you have not checked it out, please check it out. Okay. Next, let me show you some examples so that you understand this. Usually the symbols are U is basically object coordinate. V is basically usually the image coordinate. R is basically the coordinate of center of curvature. F is the coordinate of focal point, right? So these are basically the symbols which you will be using in general for mirrors or lenses: focal length, radius of curvature, V, U. So they are the coordinates. Actually, they are not the distances, they are the coordinates. So what do I mean by that? Let's take an example for that. Say this is our mirror like this. This is a convex mirror here. Then let's say this is another convex mirror here. Let's say this is a concave mirror over here. There is another concave mirror over here. Now we all know the principal axis will be basically dividing it in two equal parts, right? Now let's say I place the object. Let's say I place the object and my object is somewhere over here. This is where my object is. This is where my object is. And let's say the image is formed over here. The image is formed over here. Let's say here is where the image is formed. Let's say here I have placed an object. Let's say here I have got an image. Let's say here I have placed an object, and let's say here I've got an image. So these are some random cases that I have chosen, okay, for us to figure out what the sign convention will be. What the sign convention will be in all the cases. Okay, let's try to figure it out. First of all, always see where the incident light rays are going. Where the incident light rays. Or from the object, they will always start like this, correct? From the object, they will always start like this. From the object, they will start like this. So I will just show the incident rays so that we have perfect clarity. So from the object, they are going to come like this. This is how the incident rays are going to come. The pole is always the origin. The pole is always the origin, and wherever the incident rays are going, that side, whichever side they are pointing, that side becomes positive, which means in all these cases, incident light is going this way, so this side is positive. Incident light is going this way, so this side is obviously positive. Okay, incident light is coming this way, so this side is positive. Incident light is coming this way, so this side is positive. Naturally, the other side will become negative. So this is the negative side, even this is the negative side, this is the negative side, and this is the negative side. Is this absolutely clear, my dear students? How we decided which side is positive, which side is negative? Next important thing, my dear warriors, observe carefully. Where is the center of curvature going to be? Well, the center of curvature of this imaginary sphere will be somewhere over here. And let's say the focal length, Chumma I'm putting somewhere, okay, is over here. Maybe the center of curvature is over here. And maybe the focal length is over here. Focal point is over here. Maybe, I don't know, Chumma I'm putting, maybe the center of curvature is here. Maybe the focal point is over here. Maybe the focal point is here, maybe the center of curvature is over here. I've just put some random locations. Okay, now let's figure out what the signs are. Now let's figure out what the exact signs are for object distance, image distance, object distance, image distance, object distance, image distance, object distance, image distance, and next for radius of curvature, focal length, radius of curvature, focal length, Same thing over here, radius of curvature and focal length, radius of curvature and focal length. Okay, let's start with the object distances first. Let's start with the object distances first and image distances. Here the object is on the red line, negative side, so 100% it is negative. Image is on the green side, yes, it is positive. Here the object is on that red line, yes, object coordinate is negative. Image is also on that red line, so negative. Here the image is on the green one, so V will be positive. Object is on the red one, so it is a negative, correct. And similarly over here, object distance will be negative because it's on the negative side, and image is on the positive side. So that's how I figured out the sign convention, everyone. Now, talking about the radius of curvature and focal length, what did I tell you? For radius of curvature, check the coordinate of center of curvature. For focal length, coordinate of the focal point. So for R, see where the C is. For R, radius, check where the center of curvature is. It is on the green side, so it is positive. Focal point, it's on the green side, so it is positive. For R, for the radius of curvature, what will you see? You will see where the center is. Center is on the negative side. Focal point also on the negative side. Here, the center of curvature and focal point both are on the negative side. So this is also negative and this is also negative. You can see it's on the red side. Here, focal point, center of curvature is both on the positive side, guys. So this will be positive and this would be also positive. That's how you do it. Everyone clear about this? Everyone clear how to solve these kind of questions? Yep. Awesomeness. Perfecto. Great. So that is basically regarding the sign convention, pole, optical center, principal axis, focal point. Now, what is this focal point also? We'll come to that because I think we had not defined it formally, although you might remember it from your 10th standard. Well, when a parallel beam of light is incident on mirrors, then the rays basically either converge, the reflected rays converge at a point F on the principal axis of a concave mirror, and for a convex mirror, the reflected rays appear to diverge from a point F on its principal axis when a parallel beam of light is incident. So that point is called as F, which is called as the principal focus of that particular mirror, and the distance from the focal point to the principal axis is called as the focal length. Yes, the distance between the focus and the pole is called as the focal length of the mirror. Very, very important. So just going back over here, let's say we take a parallel beam of light. Can I take a parallel beam of light? Little bit difficult, but can I do something? Yeah, maybe over here. See, the rays are almost parallel if I make it go really far away. And you can see that wherever the rays meet, after or appear to meet, that is very close to the focal point. Same thing for a concave mirror. I know this is not very close, but if I take it really, really far, then the rays approximately try to meet somewhere here. That is where the focal point is going to be. Okay, I unfortunately cannot show parallel beam for some reason over here. Yeah, I can't do that. I'm so sorry. But I'm pretty sure you get the idea. For a concave mirror, it will meet. For a convex mirror, it appears to meet. It will not physically meet. Okay, so that is where the focal point is. From focal point to the pole, that distance is called as the focal length. The symbol for that is basically small f, like I had mentioned before. Now, also very important, this particular thing, which is nothing but f is nothing but r by 2. Very, very important, which means, observe this carefully. If this is your focal length, this focal length is exactly half of the radius of curvature, or f is the midpoint of center of curvature and the pole. Same thing over here. If this much is basically f, then this much is basically r. F is always radius by 2, or f is the midpoint of center and the pole. Very crucial result which you need to remember. R is 2f, f is r by 2, whichever way you want to remember it. If you know radius, you know focal length. If you know focal length, you know the radius. So that is that relationship which has been mentioned over here. Okay. Now, I am interested to figure out where exactly, sir, is the image formed. Now, if you notice over here, I can draw few rays and see where they meet. If the rays actually meet, can you see? The rays are actually meeting. Let's draw it again. See, the rays are meeting. Again, let's see it. The rays actually physically meet here. When they physically meet, the image is real. But let's say if I place the object over here and then see what exactly is happening over here. In this case, the rays don't physically meet. Observe it carefully. After reflection, they are not physically meeting, they are diverging. So I had to extend it behind. So this image is obviously a virtual kind of image. Obviously, it's behind the mirror, so it is virtual. But if the image was in the front of the mirror, then it would be real. So this is the real side, this is the virtual side, because it is behind the mirror. Behind the mirror, nothing can go. So it is the virtual side. In front of the mirror, things can meet. So that is why it is the real side. Correct? Okay. So, sir, you are drawing ray diagram. Yes, I am drawing ray diagram. If you see, one ray is going parallel after reflecting from the mirror, it is passing through the focus. Another ray, I'm showing it, probably going through the focus. And because it is passing through the focus, after reflection, it is becoming parallel. Another ray, I'm showing it incident over here. It is exactly the midpoint. So it will symmetrically reflect back like this. You can see all these rays are meeting here. In fact, if I show many other rays also, they will meet exactly at the same point. Not all the rays get utilized, obviously, because some of the rays will escape that reflection. They will not be a participant in that reflection. Few of the rays will be. But what difference does that make? Does the number of rays matter really? Answer is strictly no, because whether I make the mirror small or whether I make more rays participate in the reflection, the image is still going to be formed at the exact same place. I take a small mirror, I take a medium mirror or a large mirror, the image is still formed at the same place. So what does the extra rays participating in the reflection ensure? You will see that the image becomes brighter because more rays converge, more rays are participating, so the image will be more crisp, clearly visible. It will not be a faint image, it will be a bright image. So the moment I make the mirror small, few rays are participating, so the image might become a fainter image. The location won't change. Is this absolutely clear, my dear warriors? What effect does number of rays have, and what does the effect of size of mirror have on the image location or the image intensity? Bigger mirror has an effect of intensity being increased for the image. The actual location of the image won't change. Okay, the actual location of the image won't change because of the size of the mirror. Yes, the size of the mirror has only effects on the brightness or the dimness of that image. Where the image is formed depends on where the object is placed or how much is the radius of curvature and all of that. That will decide where the image is being formed. You just need two rays. Actually, you don't need many rays to locate where the image is being formed. This particular method of showing the rays and locating the image, do you have some kind of deja vu from 10th standard? You might have done it and you would have fancied it like anything. Sir, ray optics was my favorite chapter, sir, because you know why? Because we used to draw these rays, we used to show them getting reflected, one is passing through the focus, the one which passes through the focus becomes parallel and all of that, or the ray which hits the pole gets symmetrically reflected. In fact, one more ray is there. If you make it pass through the center of curvature, it will come back via the same path. Yeah, that is the speciality of the rays which go through the center of curvature. They will not deviate, they will just retrace back the same path. So you would have done this back in 10th standard, yes or no? Yeah. Rafa Banu, I'll be making a strategy video later on physics, don't worry. Okay, on how to improve your scores from average, below average to 120, 140 zone very soon. Do you remember this? Yes or no? Drawing these ray diagrams. Perfect. Some of you do, some of you don't. Okay. But I hope now you remember what I mean. Okay. Clear? Now, usually in your NEET exam, obviously you don't get an answer book where you draw the rays and see where the rays are meeting. So you cannot use the ray tracing method. Like for example, this particular way. We can take any two rays from a point of an object, trace their paths, find the point of intersection, and thus obtain the image of the point due to the reflection of that particular mirror. Like one of the rays could be the ray which is parallel to the principal axis. The reflected ray goes through the focus. The ray passing through the center of curvature of a mirror passes through it, uh, basically retraces the same path. Retraces basically the same path. The ray which passes through the focus, the ray which passes through the focus or appearing to pass through the focus, the ray becomes parallel to the principal axis. All these were the rules basically for your ray tracing, which is exactly what this particular simulation is showing. Be it concave mirror or even convex mirror, you can just show some rays and see how they are exactly tracing out, and wherever they appear to meet or actually meet, that is where the actual location of the image is. That was the ray tracing method, correct? But you cannot use this method in the NEET exam unless there is a diagram based question. Usually you will be given distances, how far it is, what is the radius, what is the focal length, where is the image, what is the size of the image. So there is a formula for it directly, and there is a small derivation which is also mentioned in your books. But for a NEET exam, you don't need those derivations. So there is a formula which goes by like this: 1 by V plus 1 by U is 1 by F. 1 by image coordinate plus 1 by object coordinate is 1 by focal points coordinate. This is also called as the mirror equation or mirror formula. What is this called? This is called as the mirror formula or the mirror equation. Directly by substituting values without drawing these rays, you automatically get where the image is. That's the beauty of this formula. Keep in mind, these are sign sensitive equations, meaning if you miss a sign, you will get a wrong answer. So you cannot make a mistake probably. Not just that, if you notice one more thing, this image which is formed sometimes is small, sometimes you might also see it is inverted, sometimes you might see it is erect like this, it's upright. So different possibilities are there. So that has been defined by a term called as how much magnified it is. For example, over here, don't you see the image is magnified? 100%. Now, do you see that the image has been compressed, so it is diminished? But now again, the object is here, this is the image has become enlarged. Similarly, convex mirror, you can see that this is the object, this is the image has been made smaller, the image is diminished in nature. So how big the image is with respect to the object is given by the term called as magnification. How much magnified it is. If I say it's magnified 5 times, that means that means whatever the object is, the image is 5 times more than the object. If I say the magnification is half, that means the object is basically 1 unit, this is half unit, this is half of the object's height. That is the meaning of magnification being half. But you will also see magnification comes with a sign. Yes, magnification does come with a sign, positive and negative. Sometimes it can be +5 or -5. It can be plus half or minus half. What do I mean by that? If it is negative, that means the image has been inverted with respect to the object. And if the magnification is positive, that means the image is upright, erect with respect to the object. That's the meaning of the sign which comes in the magnification. So I'll put it over here. If 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 let's say, for example, magnification, the symbol for that is m, is positive, that means it is upright, it is basically upright or basically erect. If the magnification is basically negative, it is basically inverted in nature. Next important thing, if the magnitude of the magnification is more than 1, then it has been enlarged, it has been made bigger. If by chance the magnitude of the magnification is less than 1, then the image has been made diminished, it is smaller than the object. And lastly, if by chance the magnitude of the magnification is 1, then by coincidence it will be of the same size. For example, right over here, say I put the object here, can you see the image is of the same size? Yes, the image is of the same size. So the magnification's magnitude is 1, but the sign of it is negative. So technically m will be -1. M will be how much? -1. Everybody agrees with this? Why is it negative? Because it has been inverted. Why is it 1? Because size is the same. So the size is decided by the magnitude, and the sign decides whether it is upright or whether it has been inverted. Clear, my dear warriors? So the formula for the magnification, my dear students, is given over here. It is V by U with a negative sign. V by U with a negative sign gives you the magnification, which is image height by the object height. Image size by the object size. That gives you magnification. How many times is the image magnified with respect to the object? Negative of image coordinate by object coordinate. This is also sign sensitive, meaning numerator denominator can be positive or negative. Accordingly, the sign of m can change. Accordingly, the sign of m can change. Don't worry, we'll be doing questions on this now. All right. So probably here is the one of the first questions coming up on your screen. This is there in your in-text NCERT. Example 9.1. Suppose that the lower half of the concave mirror reflecting surface is covered with some non-reflective material. What effect will it have on the image? Think about it. Imagine there is a mirror like this, and you had an object over here. This was your object. So usually what would happen? The rays from the object would go like this, go like this, will go like this, like this, and then reflect also, correct? They will also reflect, maybe like this, maybe like this, maybe like this, maybe like this, maybe like this. They're reflecting, and they're maybe making a image over here. Now, what will happen if somebody removes this? Basically, they cover it with a opaque material. Then you will have fewer rays getting reflected. Only these rays will get reflected. These rays won't get reflected. Only these rays will get reflected, which are on the top. So because of which, what will happen? The image will be formed still at the same place, just that the image will be slightly dimmer. Yes, so the image will be of less intensity, but the image location will still remain intact. Correct? I think I just showed it to you sometime back over here only, when I showed these rays, and I told you, doesn't matter what the size of the mirror is, the location is the same, the intensity of the image will definitely change. Cool. Give me a thumbs up. Can we go ahead to the next question coming up on your screen, my dear students? All right. Here it comes. There is a mobile phone, okay, lies along the principal axis. Can you see there is a mobile phone right over here? In case you are not able to see, this is it. Okay, this is a mobile phone. Nowadays, we don't get the antennas separately. 20 years back, 15 years back, there were mobile phones with antennas popping out of it. So nowadays, we don't have it. Okay. Show by suitable diagram the formation of its image. Explain why the magnification is not uniform. Will the distortion of the image depend on the location of the phone with respect to the mirror? Okay. Now, basically, uh, this was the object, and the image is basically like this somewhat. The image is basically somewhat like this. The question is, see, the mobile phone was almost rectangular. Why the image has become something like a trapezium? I think the idea you will get it right from here. Just check this out. Okay. Just imagine, just imagine this is where the first part or one side of the mobile phone is. Let's say this is the mobile phone. Okay, this is the mobile phone. Where is the image formed? It is formed right over here. The image is formed right over here. Now, what I will do, I'll just shift the object over here. That means I'm trying to find where the reflection of this part will be. The reflection of this part is here and it is much smaller. If I shift this arrow mark here, I'm trying to find the reflection of this part. The image is over here even smaller. If I take it over here, the ray, then you can see the reflection is here. It is even smaller. So right from the beginning till the end, you can see every place on that big, mobile phone, whenever I try to find the reflection, whenever I try to find where the image is, the images are not of the same size because, every object distance will give a different image distance, different magnification, different size. So that's why, although the object height might be the same, the image heights will not be the same at different places. Is that clear? So instead of placing the mobile phone over here, had I placed the mobile phone over here, then the distortion will be even more different. Like if I slowly change the object locations, you can see the image is formed at different place. If I place the mobile phone over here, then maybe it will be formed at a very different place. It will be, the images are formed here, and here. You can see if I place the object at different places. So where you place it matters. Also, the magnification is different for different object distances. So that is the true answer to this. Okay, so I can just say that for this particular object, probably this could be the image. Similarly, for this particular object, maybe this is the image. That is the reason for that. Different object distances, different image distances, different magnifications. Next question on your screen now. 9.3. An object is placed at 10 centimeters, 5 centimeters from a concave mirror, radius 15. Find the position, nature, magnification of the image in each case. Okay. First things first, it's a concave mirror. Let me remind you of that. If it is a concave mirror, if it is a concave mirror, the center of curvature will be here. Focal point is the midpoint of the center as well as the pole. Okay. The object will be placed somewhere on this side in front of the mirror. So that means this will be the positive side, and obviously this will be the negative side, because the object will be placed somewhere over here. The rays from the object will come like this. The rays from the object will come probably like this. Okay, this is from the object. Okay, so that's why this side is positive, this side is negative. This sign convention should be absolutely clear. Now, can you see the radius of curvature will technically not be 15, it will be negative 15. So technically the radius of curvature will be negative 15 centimeters. Everybody with me on this? Okay. What about F? F is nothing but R by 2 So whatever 15 is there, divide by 2. So minus 7.5 centimeters. So r by 2. So that's why negative 7.5 centimeters. Correct. Oh, yes. Definitely, I'll have water after some time. Thank you so much, Krishna, for reminding me. Okay. Now, once I know F, let's do it for part 1 and then let's do it for part 2. So part 1, object is over here. So object distance will be negative 10. Object distance will be negative 10. So when I use 1 by V plus 1 by U is equal to 1 by F, U will be negative 10. F will be already mentioned over here, negative 15 by 2. You can put it negative 15 by 2 or something like this, or negative 7.5. So that would be my equation which I will be solving. How to solve such equations? Some of you usually face some difficulty because things are below, not on the top. So this will be nothing but 1 by V is equal to, take it on that side, 1 by 10 minus 2 by 15. F 15 and 10, the LCM is 30. 10 goes with 33 times, 15 goes with 32 times, so 2 2s are 4, so it will be negative 1 by 30. So therefore, the image distance will be negative 30 centimeters. Now, the moment I get the image distance, have we got negative 30? Yes. Negative 30, it clearly means the image will be formed this side in front of the mirror. That means the rays will reflect and they will meet physically. So definitely the image is going to be real in nature. It is going to be real in nature. Everyone? Great. What about the magnification? Magnification is negative V by U. So V is negative 30. U is basically negative 10. Negative, negative, negative. One negative remains and negative 3 will be the answer. This negative says that it is inverted. It is definitely inverted. But this number 3 says it has been enlarged. The size of the image is going to be big. Yes. So to show you practically how it would be, most likely it will be something like this. The object will be here. The image will be here. The object is at 10 centimeters. Check this out. Object is at 10 centimeters. Image is at 30 centimeters. Image is formed at 30 centimeters. The image has been inverted, but it is triple the size of the object. So this is approximate ray diagram of this particular problem which we have just solved. Is that clear? Yep. Now, if you look at the second part of the problem, when it is 5 centimeters, so you will take U as basically minus 5. Why minus 5? Because object will be again in front of the mirror. And then use similar logic, 1 by V plus 1 by U, U is negative 5, is equal to 1 by F. F is nothing but your negative 15 by 2. Negative 15 by 2. Solve this again just like you did it over here by taking LCM. The V value comes out as 15 centimeters. Now, because you got it as positive 15, it clearly means the image is formed on this side behind the mirror, means the image is going to be virtual in nature. Talking about the magnification, it will be negative V by U. V is 15 and U is basically minus 5. Minus minus cancels, it will become 3 times. So this means it is nothing but erect because it is positive, but it is enlarged. So most likely the possible diagram for that would be something like this. It will be like this. The object is 5 centimeters in front of the mirror. Object is 5 centimeters in front of the mirror. Image is 15 centimeters. 15 centimeters behind the mirror. It is virtual. You can see it is erect and it has been magnified. It has been magnified how much? 3 times. It has been enlarged 3 times. Clear? So this is how it is. So I hope you are getting a feel of the NCERT problems as we are solving. I'm demonstrating over here how and what this actually means in reality. So we are actually feeling physics here. We are not just solving the problems blindly. We are getting a feel of what this problem might actually look like in reality. Great. Cool. So if you don't like arrow marks, you can always use penguins. Penguins are cute and penguins are rare and penguins are fun. Okay, so there we go. Okay, awesome. But this penguin is huge. It's the head is getting chopped off. Okay, but now it's not getting chopped off. Perfect. Cool. So moving on to the next question coming up on your screen, and here it is. Suppose while sitting in a parked car, you notice a jogger approaching towards you in the side view mirror. So you're in a car, side view mirror is there, and the side view mirror is usually a convex mirror. Radius of curvature is 2 meter. The jogger is running at 5 meters per second. How fast the image of the plane will be? Okay. How fast the image of the jogger appearing to move when the jogger is at 39, 29, 19 and 9 meters away. So basically at different places they have asked you what might be the approximate speed of it. Okay. So here is the logic behind this. Imagine this is our convex mirror. This is our convex mirror. The object will be here, so the rays will be going like this. That means this side will be positive and this side, oops, and this side will be obviously negative side. Okay, so we have a jogger who is coming from here. So maybe the object is over here, and the jogger is, how many meters away? The jogger is appearing to move 39 meters. Okay, the jogger approaching towards you. Okay, so we are like this. This is the mirror. The jogger is coming like this towards us. So after some time, that same object might come over here. That same object might come over here. Maybe earlier, this particular distance, could have been maybe 9 meter. So technically object distance is negative 39 meters, So, after 1 second, because the jogger is running at a speed of 5 meters per second, after 1 second from 39, 39 minus 5 will be 34. So the jogger will be at a distance of how much? 34 meters. This is going to be object distance, which is negative 34 meters. So this is basically in 1 second. This is in 1 second. This is what has happened. From 39 meters, you have gone to 34 meters because the jogger speed is given to be 5 meters per second. Is this clear? Wave optics after ray optics. Probably it will take few days. Sometime next week or next to next week. Okay, cool. Till this point? Perfect. Now, my dear students, observe this very, very carefully. Because the object has moved, the image will also move. And that is what the question is, what speed will the jogger appear to me at? So what will you do? For this particular object distance, try to find where the image is. Use this formula, 1 by V plus 1 by u is negative 39, is equal to 1 by f, focal length not given. So what I will do, this is where the focal point will be, this is where the center of curvature will be. Radius, it is positive 2 meters. F is r by 2, so it will be basically 1 meter. Okay, so this is just going to be 1 over here. From this, you will get what the image distance is. You will get basically what the image distance is, and I think they have found it out to be 39 by 40. 39 by 40 meters. Do the same thing for this as an object and see where the image will be. By using the mirror formula again, 1 by V plus 1 by U will be negative 34 is 1 by F. What is the focal length? It is again plus 1 meter. Okay, solving this, you will get the new image distance, and I think the answer that they have got is 34 by 35. 34 by 35 meters. So can you see both of them are positive? 39 by 40, 34 by 35. So what it means is that the image has shifted. So the shift in the image, my dear warriors, so the shift in the image will be just V1 minus V2. Whatever is bigger, you take first. and what answer you get over here is 1 by 280, 1 by 280 of a meter. And all of this is happening in 1 second. Very, very important. So the person is moving at 5 meters per second, the jogger, but in the mirror, the person is hardly moving 1 by 280 meters in 1 second. Isn't the speed much slower in the mirror as compared to the one in an actual? Isn't the speed in the mirror much slower than the actual speed of the jogger or the object out there? This is why you will see on the rear view mirror of vehicles, they write that the objects in the mirror might be closer than they appear, because you might see them moving slowly, you might see them small, you might feel that, okay, they're small, they might be far, but actually they are much closer than what they might appear or feel in that particular mirror. That's the reason for it. Okay, then you can do the same exercise for the other distances and all of that. So that is what has been done in this particular problem. Is that clear, everyone? Okay, beautiful question. Just to make you visualize this, imagine I'm sitting in the car. This is my side view mirror. I see suddenly from Antarctica, one penguin starts running towards me. Penguin is jogging and coming towards me. What will Shreyas Sir see? Shreyas Sir will see the image of the penguin inside the car's mirror like this. And you will see that earlier the penguin was here, now it is moving here, it is moving here, it is moving here. See, this penguin, Pavam penguin from Antarctica, is running so much, but the image is hardly moving. So that is why it creates a apparent feeling that, you know, the objects behind are slower, the objects behind might be very far away, but actually see, this penguin is running so fast, but this image is hardly moving anything over here. So it might make me feel the penguin might not be fast, but actually it is very fast. Got it? Did you visualize it now? I'm pretty sure you would never have seen this demonstration before this. I know you have seen it practically in your rear view mirror, but ray diagram wise, this is what I mean, by the instructions which are mentioned on the rear view mirror. Objects in the mirror are closer than they appear. In fact, I feel there should be one more notification which should be written on your wall. Yes, just like in the side view mirror, they write objects in the mirror are closer than they appear. On your wall, what should be written is, yeah, the exam, or basically the the NEET, the NEET exam on paper may seem farther than it actually is, than it actually is, isn't it? You feel that, oh, NEET exams are 1 year is there, NEET exams are 2 years are there. That's what you thought in 11th standard, right? Then 12th standard, oh, 1 year is there. Then maybe drop year. Oh, NEET exam came and went. Okay, next year I'm going to work hard. Drop year. Okay, fine, sir. NEET is 1 year away. Then suddenly it becomes 200 days, 180 days. And then you're like, okay, sir, NEET is 5 months away. Okay, I can manage. But actually, it is not 5 months. It's less than 5 months, because you have to spare some time for revision, mock tests, strengthening your weak points. And some days might be low, sometimes you might not feel like studying, some days you might just fall sick, who knows. All those things you have to take into account, and you need to keep some buffer time. That's why you have to complete the syllabus way in advance, right? And don't worry, there is something really cool which we are going to get for you. And yeah, it's going to come up on the channel very soon on 28th of November, because most of RNA done, DNA batch almost coming to an end, and the DNA students too are very eager, sir, what's next? And yeah, the plan for them too is coming up. And all the things which you might be looking forward to might be answered very soon. So stay tuned on the channel is what I would say. Right, correct. Let's move to the next part, and that is a refraction. Okay, beautiful. Refraction is the phenomena where the light goes from one medium to the other medium and changes its path, changes its speed, changes its wavelength, but not its color. I mean, if blue color entered water and suddenly blue became green, that would be weird. I mean, imagine a fish which you take out from the water, maybe it is green in color, but you dip it inside the water, it looks yellow. You're like, what the hell? Green became yellow. Or you are swimming underwater, you are brown or white or wheatish in color, suddenly you start appearing orange. You're like, oh, Shreyas sir, underwater you look orange, sir. No, that doesn't happen. So frequency of the color, frequency of the light does not change when the medium changes, but it's the speed, the path, the direction changes, even the wavelength changes. So this phenomena of bending, changing the path of the light with the speed is called as refraction. Okay, so yeah, so I think I can mark few things. A beam of light enters another transparent medium. A part of the light gets reflected. Part of the light gets reflected into the first medium, while the rest enters the other. Okay. This phenomena is called the refraction of light. Snell's experimentally obtained the following laws. Okay, and also mentioned over here is the incident angle, which is less than 90 degrees and more than 0 degrees. So what are the two laws which Snell obtained based on that? See, there is one medium here, there is another medium over here. You can see there is a normal drawn over here. This is the ray which is falling. It changes the direction. It was supposed to go here, but it has deviated very clearly, and the path has been changed because of refraction. So this angle is called angle of incidence, but not all the light will go here. Some of it will definitely get reflected by laws of reflection. Some of it will get transmitted, which is then called as the refracted ray. So the angle made by the refracted ray with the normal is called as angle of refraction, not reflection, refraction. That is the angle of refraction. So the first law, as per Snell, is that the incident ray, the refracted ray, and the normal are in the same plane. Makes sense. Everything has to be in the same plane. It would be very weird if light is coming like this and the light after entering water is going somewhere else only, and normal is somewhere else. It doesn't make sense. So it has to be in the same plane. Okay, next important thing is if you measure the sine ratio, trigonometry, sine, cos, tan, cot, sec, cosec, that one, sine of the angle of incidence and the sine of the angle of refraction, and you keep on introducing different angles of incidence, it will keep on getting refracted at different angles. Every time the ratio of sine of incidence and sine of refraction is a constant value, which is called as the relative refractive index. This is called as the refractive index of the second medium with respect to the first medium. Some books use the symbol n, some books also use the symbol mu, and you can write it like this, mu 1 2. So when I put like this, it is the same as n to 1, very confusing. When I write 1 mu 2, it means light has gone from medium 1 to medium 2. Light has gone from medium number 1 to medium number 2. But while saying it, you will say refractive index of 2 with respect to 1. Got it? Just like when you have velocity 2 1. What do you mean by it? Velocity of 2 with respect to 1. Same way over here also, this is a refractive index of 2, refractive index of 2 with respect to 1. That is how it is pronounced, but while writing you will write 1 mu 2 or n 2 1. So it's up to you which convention you want to use. Everything is the same thing, depends from book to book, and your NEET exam and TA paper can have any of the symbols. It doesn't really matter. Okay, now this constant that is there, it depends on what is the medium here and here. So if I, instead of water, I use glass, it will be very different constant. If I use diamond, it will be very different. If I use glycerin, it is different. If I use some plastic transparent type, it is very different. So this ratio which I got is constant. That constant depends, that constant basically depends. It's a characteristic of the pair of the media. And I say pair means both. Not just this, it also depends on what is there on medium one side. If instead of here air, If you use some other gas, maybe some smoke, it might be different. If it is vacuum, it might be different. If it is water, it might be different. So both of them, both means pair. So it depends on the pair of the media. And you will see it is independent of the angle of incidence and also depends on the wavelength. That will come to it later on in the concept of dispersion. Okay. So having said this, let me also tell you the different things over here. There are few formulas. I will make you understand this. Yeah, like this. Okay. Uh, Usually the refractive index to 1 means light went from 1 to 2. That is how it went. Light went from medium 1 to 2, which is said as refractive index of 2 with respect to 1. This is relative refractive index, but it can be also written down as mu2 by mu1, where these are absolute refractive indices of the medium. When I say absolute refractive indices of the mediums, meaning it is with respect to vacuum. It is with respect to vacuum. Usually light might enter from air. Air is almost as good as vacuum only. So you can say anything measured with air or vacuum approximately is absolute refractive index. Usually light will come from some bulb in our surroundings, atmosphere. So we measure everything with respect to air or vacuum. So that's why we have this term absolute refractive index. Light entered from air to glass, light entered from our surrounding to diamond, light entered from something to a transparent, some maybe a plasticky sheet or some translucent medium, amber glass, thing like that. So that's why we have this term absolute refractive index, which is mu2 by mu1 is 1 mu2. 2 goes on the top, this 1 goes over here below. Keep that in mind. And you can therefore also say if 1 mu2 is mu2 by mu1, 2 mu1, 2 mu1 will be mu1 by mu2, which is exactly opposite of this. So I can always put a reciprocal over here and I can put 2 over here and 1 over here, which means if light went from 2 to 1 instead of 1 to 2, then the refractive index relatively will be reciprocal of the previous one. Kind of makes sense. If you reverse the direction of light, obviously the refractive index will be a reciprocal. That is what has been even mentioned over here. N12 is N21. Okay, don't get confused. Right? Clear? Also, as per Snell's law, what did we write over here? Sin I by sin R, right? So this is also equal to sin of I by sin of R. Not just that, let me also tell you, it is speed of light. It is also speed of light in the first medium upon speed of light in the second medium. These are basically speeds of light in different medium. But we also know speed of light, is frequency into wavelength. But frequency won't change. So f into lambda, f will be the same. Frequency is going to be the same, but obviously wavelength changes. Wavelength definitely will change. Keep that in mind. Wavelength will change. So this is the main formula which you should know. Main formula which you should definitely know. Now think like this. If you have things like this, okay, this is an interface. Let me also show a normal. Let's say there is a light ray which goes from this medium and bends like this. Second case goes like this and goes like that. Obviously, this would be the angle of incidence, this would be the angle of refraction, this would be the angle of incidence, this would be the angle of refraction. Obviously, this was medium number 1, this was medium number 2. Light is going from 1 to 2. Sine of I by sine of R is 1 mu 2. Speed of light in medium 1 by speed of light in medium 2. So this relationship holds true. What is different in both of them is that here the refracted angle is less than I. So R, the refracted angle, is definitely less than I. Here the refracted angle is more than I. So here I can say it bends towards the normal. Bends towards the normal. Whereas over here it bends away from the normal. It bends away from the normal, as you can see over here. It bends away from the normal. In such cases, when it bends towards the normal, I would say this is relatively a denser medium. This is relatively a denser medium, and this is relatively a rarer medium. When it bends away from the normal, then relatively this is a denser medium, and when it bends away, then this is said to be a relatively rarer medium. Now, when I say rare and dense, don't think density in terms of kg per meter cube. The density which I am referring to over here, which density is it? It is optical density, which is way different than your normal kg per meter cube density. That is mass density. This is optical density. There is no unit. It is just a qualitative term. So whenever you bend towards, it's denser optically. Whenever you bend away, it is relatively less dense or rarer. So that is the reason why you will see this note. Optical density should not be confused. That's why they have mentioned this. Optical density should not be confused with mass density, which is mass per unit volume. It is possible that something might actually have more density, but optically it is less dense, and vice versa. And for that they have given an example also, which I feel it's better to remember. For example, turpentine and water. The density of turpentine is less than that of water. If you measure in kg per meter cube, for water it is 1000 kg per meter cube. Turpentine it is slightly less. But optically it is more dense, meaning if light enters turpentine, it will bend towards the normal. Although the density of turpentine physically kg per meter cube is less, because the density which we are referring to in ray optics is optical density and not the kg per meter cube density. Clear? Also keep in mind, when this thing happens, when it enters a denser medium, the speed becomes less. The speed becomes less. Yes, it will have less speed over here. Not just that, because it is entering a denser medium, the wavelength is also going to be less. Because if speed reduces, even the wavelength will reduce. Whereas over here, you will see the speed will be more, and even the wavelength is going to increase. Because it is entering a rarer medium, it will fasten up and the wavelength will also elongate. That is what will happen. If you ask me the refractive index relatively, over here, the relative refractive index, because it is going to a denser medium, it will be more than 1. When it goes to a rarer medium, the relative refractive index will be less than 1. So whenever refractive indices are more than 1, you are entering into a denser medium. If it is 0.8, 0.7, 0.6, you are going to a rarer medium. Correct. I'll just drink some water, just write it down. Thank you, Krishna Madhumati. Thank you so much. Great. So we have understood now how refraction works over here. Now there is one more thing over here which you should definitely know, and this can be useful in some cases. Say for example, um, if you have something like this, refractive index of, let's say you have to find of A with respect to B. What you can do is, yes, you can write it as mu B by mu A. That is one way. You can also write it like this, mu. You can multiply as many terms as you want. I'll just put it some examples over here. I can put even 4 terms, doesn't really matter. Just see who is the first term. First term is A, right? So start with A. Start with A. Last alphabet is B. So put B towards the end of a chain. And all these refractive indices are basically multiplied, let me tell you. Now in between, you can form a chain. Say for example, you can just say this is C. So it will be C over here. Okay, A to C, C to B. You have to jump like a chain from A to C, then from C to, let's say, D, from D to, let's say, E, and from E back to B. So you can form a chain, and this can be very helpful whenever you want to convert from one thing to the other. Okay, you know refractive index of something with respect to something, you have to find it with respect to something else. So this chain rule you can definitely use. So this is something like your chain rule. You can make this chain as long as you want. Okay, so that also I think has been mentioned somewhere over here. Yeah, this one, this is that chain rule. This is basically that chain rule in that NCERT paragraph. They have not mentioned it, okay, but still telling you. All right, all right. And here also all these things are mentioned, which we have talked about, rarer, denser, and all of it right over here. Rarer, denser, what happens to the speed wavelength, everything has been mentioned over here in a very small way, but I have obviously explained it to you very neatly. Okay, let's see the example of refraction, of course, but for that, let me go back. Okay, refraction, where the hell is refraction? Right over here, bending of light. Cool. Let's see. Okay, there we go. As you can see, I have a torch. I can turn on that torch right over here. If you want, I can also measure the angle and all of it. I think that tools also they have mentioned if you want to measure the angle properly, but it's okay. I don't want to measure it. Just keep it here. Uh, you can see I can select different materials, air, water, glass, some unknown material A and B, and you can choose your own material. Right now it's air. I can choose this side also, air, water, glass, some mystery material or my own material. Right now it's water. Let's turn on the light. You can see the light falls here, gets reflected, some of it, and the rest of it gets refracted. It might not look very apparent to you that the light has got bent, but actually the light has got bent. Let me show it to you like this. Now you can see very easily. See, this is the angle of incidence. This is angle of refraction. It is obviously less than the angle of incidence, so it has bent towards the normal. So definitely this is a denser medium. This is a rarer medium. Now just see what will happen. Instead of this being rare and this being dense, I flip it. Maybe I make this also water. If I make this also water, it is in water only. So it will not get refracted, of course. But if I make this as air, can you see it is bending away from the normal? So now this is a rarer medium, this is a denser medium. Yeah, some of it is getting reflected, the rest of it is getting refracted over here. I can change back to the same medium. Now it is getting again closer towards the normal. If I change this medium to, let's say, glass, you can see the angle of refraction has changed. In fact, let me choose it as custom. See this, if it is air, it doesn't bend. As I increase the refractive index, the light bends more and more towards the normal. and it is more apparent if I keep a large angle of incidence. Then you can see as I increase the refractive index, it bends more and more towards the normal, right? Very, very clear. Same thing I can do opposite also. Let's say you are in that custom material and you are coming out in air. If I make this denser, you will see, if I make this denser, you will see it will bend more and more away from the normal if I make it more dense, right? That is what is happening. Awesome, awesome. Now there is a problem. I'll tell you what the problem is. And we are going to come to that as well. I think it is on the next slide. Yeah. Oh, actually, it will come later on. First, they have explained about that phenomenon of apparent depth and apparent height. So you might have seen that if you enter a swimming pool, uh, if you look at the depth of the pool, it feels that it is not so deep, or the lake, you might feel it is not so deep. Or suddenly when you put your feet inside water, you feel that your feet has got compressed. It's much smaller than what it is actually. So this apparent notion is called as apparent depth and apparent height concept. So if you are in a rare medium, seeing inside a denser medium, it appears closer. So keep in mind. So if you are in a rare medium and you look at an object in the denser medium, so the observer is in the rare medium. The observer is in the rare medium. Then what happens is the denser medium's object comes closer. So this is where the object is, but the image will come over here. It will appear to be closer than what it actually is. If it is very deep, this is the actual depth h0. This is the actual depth h0. This then becomes h1 or h prime, which becomes the apparent depth. And this apparent depth, this particular apparent depth happens to be the actual depth by the refractive index, by the refractive index of the dense medium with respect to the rare medium. So that is how it is. H prime is actual depth, whatever the actual depth is, you divide it with a number more than 1. Refractive index of glass, etc., 1.5, 1.3. So you will see the apparent depth will be smaller. This one was the actual depth. Got it? The reverse also holds true, by the way. The reverse also holds true, meaning, say for example, if there was an observer inside the denser medium and that person happens to see some object right over here, so technically this would be the actual this would be the actual height, but the image will be formed over here. The image will be formed over here. This will be the apparent height, and this apparent height will be actual height. Instead of dividing, now you will multiply refractive index of the denser medium with respect to rarer medium. So this is what happens when you are in the reverse mode. You are in the denser medium and seeing an object in the rare medium. So imagine the dynamics in nature and how beautiful nature is. A fish which is being hunted by a bird from above the surface. When the bird sees the fish appears to be closer. The bird thinks, oh, the fish is here, but when it dives, I mean, it's a complete flop show for the bird because, the actual fish is over here, right? The bird gets fooled into thinking the fish is not here, but rather here. So it feels apparently closer. The reverse of this, just think about it. The fish peacefully swimming in the water feels the bird is really far away. But as it comes close, then it realizes actually it was not far. That was the image. The bird was actually over here. So both in a way get fooled into thinking, one is closer or one is farther. And that's how the dynamics plays. But by experience, through evolution, both of them know that if the bird is seeing the fish, it's not actually there. It's much deeper. So it actually dives more. And the fish genetically, through experience and thanks to the forefathers and evolution, it knows that if the bird is over here, it's not actually there, it's much closer, so it will go much deeper inside the water. So it's now a battle of who is going to be the smarter one and stronger one. So survival of the fittest and the smartest actually. Okay, so that's what it is, which has been mentioned over here, the concept of apparent depth right over here. Okay, something which you should be aware of. Just block the formulas just in case you've not done that yet. Okay, this is when you see inside the denser medium. This is when you see in the rarer medium. Observers are at two different places. Okay, now the next limitation comes of refraction, and this is also very interesting. Abhishek, I'll be coming to the Karnataka channel. Just give me some time. Just give me 1 or 2 days. Lot of things are there. I'm trying to wind up as much syllabus as possible on all the channels and coming there. Don't worry. Luckily, Gopika ma'am, Diksha ma'am, everyone, and Baswa sir, everyone are taking classes. So I'm held up at many places. Like, I just don't have one channel. I have 4 channels to take care of, plus the crash courses which are going on. Okay. Let's go to the next point, which is basically the total internal reflection. Now, my dear warriors, what is this phenomena? I'll explain this to you very simply and beautifully. See, if the light goes from a rare to a dense medium, like over here, there is no issue at all. No matter what you choose as the angle of incidence, the light will always go into the next medium. Light is always going into the next medium, no matter what you choose as the angle of incidence. So always the light gets refracted into the other medium. But the problem happens in the exact reverse way. Just imagine if this is air and this is dense. Okay, this is something like, say, over here. Now, okay, for small angles of incidence, it is fine. For small angles of incidence, it is fine. It is getting refracted. But check over here. After this point, I can see the refraction does not occur. Only reflection occurs. You can see it is behaving like a mirror. So, two different mediums can behave like a mirror if you choose a large enough incident angle and if the refractive indices are really different for those two mediums. So, as you can see, if I choose a normal medium with a very small refractive index, the angle till which refraction occurs, okay, somewhere over here, yeah, that's it. Till here about refraction occurs, after this refraction is not occurring. So this is the critical angle for that pair of media. It's the angle till which refraction occurs, beyond which refraction doesn't occur. That is called as the critical angle, and it only happens when light goes from dense to rare and never from rare to dense. Keep that in mind. If I choose a more dense medium from which light is entering, then the critical angle will be even more less. Check this out. Now you can see the critical angle is way less. So it started reflecting right over here. See, that's it. After this, there is no more refraction, only light is getting reflected. But if I choose a normal other kind of medium, then the light will definitely refract. I will need a much higher angle of critical incidence so that it only gets internally reflected. So when this happens, light is getting reflected internally in the denser medium. This phenomena is called total internal reflection, TIR, total internal reflection, which happens after the critical incidence, Is this absolutely clear, everyone? So I can definitely then say over here, let's say like this is the medium interface. Let's say this is the normal. Let's say this is dense. Let's say this is rare. And let's say we're talking about the critical angle. So light goes like this, and that's it. It is just going like that. After this, you choose any other angle. Let's say like this. it will just get internally reflected. So there is definitely total internal reflection. But before this, if you choose any other angle, the light used to come out also. Not just that, it also used to get reflected. So both were happening before that angle. So definitely this particular angle is our critical angle of incidence, and when that happens, the angle of refraction is 90 degree. So sine of IC by sine of 90 will be, light is going from dense to rare, so refractive index of rare medium with respect to dense medium. Sine of 90 degrees is basically 1, and usually you never get refractive index of rare medium with respect to dense. Usually it is the other way around, like refractive index of glass with respect to air, water with respect to air, never air with respect to water. So whenever we have to reshuffle these variables over here, it is a reciprocal, and that is something which I gave it to you over here itself, right? 1 mu 2 is 1 by 2 mu 1. So you can just flip it around, and it will just become 1 by mu of the dense medium with respect to rare medium. So basically sine of that critical angle is 1 by refractive index of that particular dense medium. That's it. That's the formula, guys, which you should definitely know. Okay, I hope this is absolutely clear. Cool. Now, different refractive indices, everything are given on the next table, and their critical angles. Notice how for water the refractive index is 1.33, for some glass it is 1.52, for some different kind of glass it is 1.62, for diamond it is 2.42. As you can see down the chart, the refractive index keeps on increasing. Which means, going back over here, this value is increasing. That means the denominator is increasing. So the ratio will decrease, which means the value of the critical angle on the left hand side should also decrease. So that is exactly what you see. Although the refractive index increases, the critical angle decreases from 48 to 41 to 37 to 24, because it's reciprocal. Can you see that? Reciprocal. Yeah. If mu increases, I will decrease. So a more dense medium like diamond or flint glass will have a smaller critical angle. So the probability, the chance that the light might escape it is less. Very critical, guys. Observe this very interesting thing. If something has higher refractive index, then there is a greater chance that light may not escape it. Like, see this, if this is water, till here you can see the critical angle exists. If it is less dense, it is still refracting. If it is more dense, it's already internally reflected. So a dense medium will have a smaller angle of critical incidence, so it will reflect very easily. There are so many options for getting it reflected internally. But when the medium is not so dense, the options are not so many. Only few options are there for which it will get internally reflected. Other than that, it will refract itself. So that is the reason why once light enters the diamond, it will not easily come out of the diamond. It will get reflected many times. And once multiple reflections occur, that's the reason why the diamond will shine eventually when the light enters your eye. Got it? Why the diamond shines is because of multiple internal reflections, right? Total internal reflections. And there are many applications also based out of it. Prisms used to deflect light by total internal reflection, such that the light will not exit out. So this prism is particularly very interesting. This prism has no mirror, but it is acting like a mirror because the refractive index of the prism is very high. Observe this carefully. Prism is basically a cut piece of a glass, looks like a triangle. Prism shape everybody knows. So if the light is entering, once it has entered the medium of the prism, it's in the denser medium. As you can see, this is the angle of incidence, but if the refractive index is high enough, then it will not be able to exit into the air, rather it will get internally reflected. So it is getting totally internally reflected. So the surface of the prism is as if acting like a mirror, as if acting like a mirror. So the prism is used like a mirror, and this is also used in many cameras, telescopes, microscopes to change the direction of the light. In fact, the direction of the light can be even reversed using a prism, something like this. Check this out, light enters inside the prism. This is the dense medium. As you can see, if you draw normal, this is the angle of incidence. If the refractive index is high enough, then the critical angle criteria is met, then it will not enter the air medium, rather it will get internally reflected and again gets internally reflected. So it has turned by 180 degrees. So you can turn the direction of light which was coming towards you, it has been sent back via a prism. So all these are some beautiful applications of prisms and total internal reflection. So this surface has acted like a mirror, even this surface has acted like a mirror. So designed a prism designed to bend light by 90 degrees or 180 degrees using the concept of total internal reflection. Another concept is the concept of optical fiber, where if you have a broadband connection, telephone connection, or in general, even the audio signals from your speakers of TV and all of that, they use these optical fibers because normal electrical, copper, aluminum wires, they can get interference from outside signals. They might lose some energy because of the resistance of the wire, some wire touching happens, there is some cross connection which is happening, so all noise might come, some voltages might interfere, so there is a lot of disturbance and unwanted losses which might happen in regular wires like copper and aluminum. So the counter to that is optical fiber. Light will not get interfered because another light is passing. Light will not worry about electric currents, light will not worry about magnetic fields, light will just pass as if nothing bothers it. So using light you can transmit signals. That phenomena, sorry, that application is called as optical fiber. So inside that fiber, light will enter and it will get totally internally reflected until it exits out on the receiver side. And it is chosen, the material is chosen in such a way that it has very high refractive index. So whenever light falls, the angle of incidence is such that it is more than the critical angle, it gets internally reflected every time, and you can see the signal, whatever is there, the light information is being carried from one side to the other side. So they are made of high quality composite glass or quartz fibers, and basically the refractive index is higher than the cladding, and the signal goes from one end to a and gets repeated total internal reflections along the length of the cable until it comes out on the other side. Okay, so it prevents losses, it prevents interferences, it prevents unwanted noises inside the signal. That's the beauty of optical fibers, my dear warriors. Great. So that is what that is. Cool. Let's go to the next part. Okay, so that was a refraction, my dear warriors, at plane surface. Now we are going to go to refraction at curved surface. See, we just saw if you have a medium, this is the normal, then the light which enters will get refracted like this. This was angle of incidence, this was angle of refraction. This surface was basically a plane surface. But imagine a bubble, soap bubble, drop of water, or a glass which is curved, or a lens of a camera, or maybe any transparent material which has some curvature. That's a curved surface. So what happens then? So if you have a curved surface like this, some curved surface over here, okay, then what happens is as follows. Imagine this is that curved surface, this is that medium, Then what you should do in such cases, if light is entering at a point, first of all draw a normal. Let's say our light was entering maybe like this. Then this particular angle becomes the angle of incidence and the light will get refracted over here, and this will become the angle of refraction. Again, it will follow Snell's law over here. Observe one more thing, that this curved surface, which you can see over here, I hope, also will have a center maybe somewhere over here, and it will also have some kind of radius of curvature. This is your radius of that curvature. This will be center of the curvature, and this point over here is then the pole. This point over here is then the pole, and this side might have some refractive index, let's say mu1. This side might have some refractive index, let's say mu2, and the light might get refracted depending on what is the value of mu1 and mu2. Are you able to see this? Are you able to visualize this? This is called as curved surface refraction. It also follows Snell's law. Obviously it has to, because every point on that curved surface is like a flat surface where you can apply our Snell's law. Beautiful, isn't it? Now imagine you have placed an object in front of such a curved surface. Then where the image will be formed will depend on what is the radius, what is the refractive index, where the object is placed, and so many things, and you have to do ray tracing, which is very difficult. So just like we did over here, where did it go? Yeah, we did ray tracing and seeing where the image might be formed, but that is obviously not what we intend to do in the exam, because you can't sit and draw rays and the angles might be crazy. So there is a formula for it to avoid the ray tracing, and the formula goes as follows, just putting it up over here. The formula is over here. N2 by V minus N1 by U is equal to N2 minus N1 by R, and using this formula you can figure out where the actual image will be formed. Don't worry if you did not understand this particular formula, I'll explain this to you. Say, for example, and this is very, very important, just follow me over here carefully. This is some medium over here. Okay. And let's say the refractive index of this particular medium is, let's say, 3. Chumma have taken some value. And the refractive index outside, it is basically 1. First things first, let's draw the pole. Pole is basically this midpoint. Okay, let's draw the principal axis which divides it equally. This is my principal axis. Okay, now I'm going to place my object. I'm going to place my object somewhere over here. Let's say this is where my object is. Okay, so this is my object. Okay, obviously object distance is always measured from the pole, so this is u. You will see where the rays are going, and maybe the image is formed somewhere here inside, maybe chumma I'm saying some random thing. Okay, this is where the image is, so definitely this is the image distance. Can you also see the curved surface? It will have a curvature. It will have a curvature. So this then will become the radius of curvature. This will become the center of curvature. Are you able to see that? Radius of curvature, center of curvature, and all of that. Clear, my dear warriors? Now, from the object, tell me, how will the rays come before refracting and making the image? The rays will basically come like this, right? They will go like this, right? So if the rays are going like that, pole is always the center. That means right side of the pole, that means this side is positive. Obviously the other side will be negative. Obviously the other side will be negative side. So clearly the object distance will be negative because it is on the negative side. The image distance will be positive. For the radius, check where the center is. It's on the positive side. So radius of curvature will be also positive. Sign convention clear? Everybody give me a thumbs up. Harish, as of now, there is no plan for that because usually students prefer 12th standard NCERT rather than 11th standard. But I know 11th standard NCERT is also important. That's why I've done the RNA series where I might not have done directly taking an NCERT in front of you, but whatever theory was there, in fact, more than that only have given for 11th uh, topic-wise content in the RNA series. Okay, Harish? So if you're referring to my RNA series, trust me, you are doing more than what is required from NCERT. And anyways, in the board exam, 11th standard will not come. But yeah, from a NEET point of view, NCERT is important, which is already done as a part of RNA. Okay. Now, how the formula goes is this one. So let me write it down for you. It always goes second medium by image distance minus first medium by object distance is the difference of the refractive indices in the same order divided by the radius of curvature. So if you see over here what is exactly going to happen, first of all, refractive index of the second medium where the incident light comes, sorry, not incident, my bad, refracted. So sorry guys. This is second medium, that means it will be refracted. So this is where the incident light is going to be. Light is coming from the object, it is incident in this medium. So incident refractive index will be 1. This will be 1. Light goes into this medium whose refractive index is 3. So mu2 will be basically 3. Is this absolutely clear in everybody's head how mu2 and mu1 are decided? How refractive index 2 and refractive index 1 are decided, correct? Next, what about V and mu? We'll come to that, but before that, in the same order, put 3 and in the same order, put 1 over here. Now, coming to what is V and U and R. V will be positive, some positive number. I don't know whatever it could be. U will be basically here. It will be negative U. So it will be basically negative whatever it is. Example minus 3 centimeters or minus 10 centimeters or minus 20 centimeters like that. And this V you will get some value. I don't know. Chuma, I'm putting something plus 5 centimeters or or plus 17 centimeters, something after substituting, and radius of curvature. This one, it's positive. So you might get some value, maybe plus r, maybe something like this, maybe plus 8 centimeters or plus 10 centimeters like that. So that will be given to you. Object distance will be given to you. Image distance will be asked, or image distance is given, object distance is asked. Main thing is substituting in this formula with the correct sign convention. All right. So this is that formula in which you have to substitute with the correct sign convention. If you do that, your job is done. Oh, in-text questions. So is it? Uh, I think the initial chapters, at least we had done it in the class, but we'll do one thing, Harish. When we do problem solving series, I will make sure that I will involve as many in-text questions also. Thank you for reminding me, but all right. So during the problem solving, which we'll be doing it in next couple of weeks, will involve more of in-text questions of 11th standard. Okay, no issues. So let's do a question on that. Let's do a question on that. Here is the question. Read it. Light from a point source in air falls on a spherical glass surface and radius of this. Distance of the light source from the glass surface is 100 centimeter. At what position is the image formed? Okay, light from a point source of air falls on a spherical glass surface. Let's basically think about it. This is our spherical glass surface. It has its own radius of curvature. We also need to show the principal axis. This will be the positive side. This will be the negative side. Okay. Where is our object? Light source is over here. This is our object. From this object, light is coming out like this. It's going on this side, so that's why this side is positive, this side is negative. And this distance, object distance, will be how much? 100 centimeter, but negative 100 centimeters from the pole. Okay, I want to know where does it meet. And before going ahead, yes, this is the center of curvature. The radius of that curvature is 20 and it is on the positive side. So R is plus 20 centimeters. Refractive index over here is 1.5 and the refractive index over here is basically how much? 1, because it is air. Correct. Okay, perfect. So let's apply our formula. Nothing great. So mu2 by V minus mu1 by U is equal to mu2 minus mu1 divided by R. That's it. All right. So let's start substituting everything one by one. What is mu2? Mu2 is where the refracted light will be. This is incident. It will refract into this medium, which has a refractive index of 1.5. So this will be 1.5. So I'll put 1.5 here. What is mu1? That is where incident light is. Incident light is in the air, so refractive index is 1. So I'll just put 1 over here. Radius of curvature, as you can see, is plus 20. So put plus 20. Object distance is basically negative 100. So just put minus 100. Image distance is what I do not know. Now you just need to solve this equation and I'm pretty sure you'll get the answer. Okay, solve this and see what is the answer that you get. If you want, you can just shift it over here. So 1.5 by V is equal to 1.5 minus 1 is 0.5. So 0.5 by 20. Negative positive goes on the other side, becomes again negative. So 1 by 100. All right, 1.5 is 3 by 2V is equal to 0.5 is half. So 1 by 40. 1 by 40 minus 1 by 100. Obviously, we have to take the LCM of 100 and 40. Actually, before doing that, let's cancel 2 everywhere. So 3 by V is equal to 1 by 20 minus 1 by 50. Now LCM of 20 and 50, that's going to be 100. 20 goes with 100 5 times, 50 goes with 100 2 times. So it will be 3 by 100. 3 cancels. So 3 by V is equal to 3 by 100. 3 cancels. So V will be basically 100 centimeters. Yes, that is what it is, and it is positive, which means the image will be formed on this side. And if it is formed here, obviously the rays will meet. So that means there will be a real image which will be formed. Real image. This side will be real, this side will be virtual. Be careful. Yeah. Yes, 𝐂𝐤 I'll be doing it in 2 lectures, definitely. Because one lecture is little tough, not for me, but from students' point of view also, because there are many concepts in this. It's a big chapter. I don't want to hurry up just for the sake of it. Okay, clear till this point? Great. So we have figured that out. Now we'll do one thing. See, now not much is actually left if you see. It's just lenses. See, lenses, combination of lenses, power of a lens, etc. Prism is there, optical instrument, microscope, and telescope. It's not like I can do it in 1 hour or even 1.5 hours. It will also take easily 2 hours. We will do this as a part of the second lecture. Okay, lecture number 2, which most likely I'll take it on Tuesday or Wednesday. Is that right? Okay. So till today, what we have done is refraction at plane and curved surfaces and how to solve the problems on it. We have also